be discussing about LLM Fine Tuning. So it is a process where we take a pre-trained model and we train it our own data with the aim of making it capable on a domain-specific task. So coming to the point as why do we need fine tuning? It is because if we retrain a model from scratch, it will be both time consuming and resource intensive. But with fine tuning, we can make the model work very well on a domain specific data with very less time and very less resources. Now let's proceed to the problem statement.
The first is the need of LLMs trained on organizational data. LLMs are pre-trained on massive dataset of text and code, but they may not perform very well on specific tasks without additional training. The second is improved customer experience. Say for example, a company wants to develop a chatbot that can answer customer questions about their own product and services. The company has a large dataset of customer support tickets which they want to use to train the chatbot. However, the customer support tickets are written in a variety of styles and formats, and they cover a wide range of topics. This makes it difficult to train a chatbot from scratch that can answer all the questions that the customer may ask. Let's discuss the solutions. The solution to the above problem is fine tuning. Fine tuning allows us to specialize a pre-trained LLM to a particular task or domain by training it on a smaller dataset of labeled data for that particular task or domain. The added advantage here is that the model is able to leverage its pre-trained knowledge while also learning the specific skills needed for the target task. Now we will discuss some fine-tuning techniques as well. The first one is parameter efficient fine-tuning, also known as PEFT. Parameter efficient fine-tuning is a technique for fine-tuning large language models with fewer parameters. This can be achieved by freezing some of the layers of the LLMs and only fine-tuning the last few layers that are specific to the downstream task. Additionally, PEFT techniques can also be used to reduce the number of parameters that are needed to be updated during fine-tuning. Now coming to the second part, low rank adaptation. It is a PEFT technique that uses low rank matrices to represent updates to the parameters of an LLM. This is achieved by decomposing the weight matrices of each layers into smaller matrices, basically 2 in number, which are then fine-tuned independently. This can significantly reduce the numbers of parameters that are needed to be updated without sacrificing the performance of the model. The third one is quantized low rank adaptation. It is basically a variation of low rank adaptation that uses quantization to further reduce the number of parameters that needed to be updated. This is achieved by converting the low rank matrices to a lower precision format such as 8-bit or a 16-bit. This can further reduce the computational cost and memory requirements of fine tuning. Let's discuss the implementation part of LLM fine tuning. The first step is installing required packages. We will be needing some packages like Accelerate, PEFT, Bits and Bytes, Transformers and TRL. After we are done with the installation, we will be importing those libraries. Some of the important libraries include Auto Tokenizer, Bits and Bytes Config, Torch and more. Now we'll be defining the model as well as the dataset and the name of the model that will be after the fine tuning process. After that, we'll be defining the QLoda parameters. It includes the attention dimension, the alpha parameters and the dropout probability. With the attention dimension, it is basically a measure of the trade-off between accuracy and parameter efficiency. The more the value, the more accurate will be the model. About LoDa alpha, it is basically a measure of the expressiveness of the model. But we cannot keep it high because it might lead to overfitting of the model. After that, we define the bits and bytes parameter. Basically here we have loaded the model in 4-bit precision. Also, the data type that we have kept here is float 16. The quantization type is kept here as non-floating type. We can also keep it as floating type. After that, we will be defining training argument parameters. Here we have defined output directory. We have set the training process as false. Basically here we have kept it as false because if we keep it true, although the training process might be enhanced or it may take less time and less memory, but it may highly impact the accuracy, hence we have kept it as false. Also, we have defined different parameters here. After this, we'll be defining the SFT parameters, which includes maximum sequence length, packing and device mapping, and which is kept as GPU for now. After that, we'll be loading the dataset. After that, we'll be loading tokenizer model with QLoda configuration, and after that we'll be checking the GPU compatibility with bfloat 16 data type notation. Once done with that, we'll be loading the base model. After loading the base model, we'll be loading the llama tokenizers and then the LoDA configurations. We'll be then setting the training parameters, SFT parameters, and then we are good to go for the final step, that is the training and saving the model. In this way, we can fine-tune a large language model, base model of our own choice on our personal data. Now let's move on to the use cases. Fine-tuning can be used to improve the performance of the LLMs on a wide range of tasks like personalized chatbot. Base large language models can be fine-tuned on organization-specific data to use it as a personalized chatbot. The second is translation. The LLMs can also be fine-tuned for translation tasks where it can be used to translate any given sentences by the user in a particular language. The third is question answering. The LLMs can also be fine-tuned for Q&A on industry-specific data. The fourth is sentiment analysis. We can also fine-tune a model to make it for analyzing the sentiments from the conversations it had with the user. Let's discuss the benefits now. Fine-tuning a large language model has a number of advantages and benefits, such as improved performance on specific tasks. LLMs are trained on massive dataset of text and code, which gives them a broad understanding of language. However, they may not perform well on specific tasks such as text classification, question answering, or sentiment analysis. Fine-tuning an LLM on dataset of labeled data for a specific task can significantly improve its performance on that particular task. Second is reduced data requirements. LLMs are typically trained on massive dataset, which can be expensive as well as time consuming to collect and label. Fine-tuning an LLM on a smaller dataset of labeled examples for a specific task can reduce the data requirements for the task. The third is transfer learning. Fine-tuning an LLM allows you to transfer the knowledge that it has learned from its pre-trained dataset to a newer task. This can be especially useful for tasks where you have a limited amount of labeled data.
Now coming to the conclusion, organizations can train the base large language models with their own data in very less time and also with very less compute power. With this, they can make their personalized chatbots. They can also increase the research and analysis of their own data, and also they can offer customers new products and developments. And they can attain much more by augmenting the power of LLMs with their own data.
With our 10 moves to make movements matter, we focused on how to help our colleagues to practice cultivation. Maverick program and roles definition created and socialized cultivation behavior to help people understand how they can bring cultivation to life and to provide them with a common language to describe actions related to cultivation. One behavior doesn't exclude another, and all XenonStack people are invited to explore the behaviors, play and practice with them to find inspiration for their own way of cultivation.